the piecewise functions. So first we're going to do a continuity review. So first, list of 3 criteria for f of x to be continuous at x equals b. Well, in step 1 is f of b has to be defined. Right, you can say it exists, whatever, it's the same thing. Number 2 is the limit as x approaches b of f of x exists. And 3, these have to equal. So f of b has to equal the limit as x approaches b of f of x. So there we go. Sketch a graphic example of each type of discontinuity and label it. Well, okay, so we have the hole. Now remember, the hole is not actually called a hole, it's called removable. We could have the jump. Probably the thing I always think of when I think of discontinuity. And then we have the infinite, which is the vertical asymptote. So there we go. So now let's get to the next part. For each piece of function, for each piecewise function, the graph of f of x. Graph f of x. So first, gotta graph it. Determine if the function is continuous using continuity criteria. Okay. If not, which criteria fails? Okay. Find the derivative analytically, then graph f of x. So that's a lot of steps here. You gotta graph it. Tell me if it's continuous or not. If it is continuous, show me the steps. You know the good like formula, just show me the steps. And then if it's not continuous, so why? What criteria does it fail? Then we're gonna take the derivative. We're gonna graph the derivative, and then see if it's differentiable everywhere or not. And if it's not, where does it fall? So that's everything we're gonna do here. Graph it, right? So 3x minus 1 when x is less than 1. So 3x minus 1, so negative 1. Slope of 3, 1, 2, 3 over 1. Now remember, 1 is where you partition, so I only want the left side of the 1. So I normally graph the whole line, something like this. And then only fill in the part that I want, which in this case would be the left side of 1. It's right to the left, because here's my x. Here's 1 on my x, so I only want the part, everything less than or left of it. That's how I normally do it, and then you can erase the rest. Okay, then this graph, 2x minus 1, when x is greater than 1. So 2, remember this is the same thing as saying negative x plus 2, it's a little easier. So up 2, down 1 over 1, down 1 over 1. So again, this will go this way. But really all I want was where it's greater than 1, it's an open circle. So like that, to the right. So there's my piecewise function. You can tell right away it's not continuous. There's a jump there. So if it's a jump, it means it has to fail criteria 2. The limit should not exist. But let's do the work here. So if I do the criteria connection, f of 1 equals 2. So that exists. The limit as x approaches 1 from the right. Let's do the right first. So plus. Again, that means that I plugged into the greater than sign, so you plug in 2 there and you get 0. I'm trying to plug in 1 there and I get 1. The limit as x approaches 1 from the left of f. In this case, you plug 1 into this guy, you get 3 minus 1 is 2. So this does not exist. So limit 2 does not equal 1. Limit does not exist. Fails criteria 2. Like that. Okay, so what's next? C and D is take the derivative. So when you take the derivative, so you literally check the derivative sign. So derivative of 3x minus 1 is 3. The derivative of 2 minus x is negative 1. This would still be x equals 1. Now these are both going to be at x equals 1. The key things and the key with these problems is, do you put the equal to sign or not? Now, because remember, we're asking is it differentiable? That's when you put it. You only put the equal to sign when it's differentiable. Well, it has to be continuous to be differentiable. So in this case, no. Anytime you're not continuous, you don't put it because it's not going to be differentiable. So for us here, we won't put the equal to sign. Because again, it's not going to be differentiable because it's not continuous. Automatically fails that one. If it was continuous, then we used to check it, so they do the limit step to see if we put the equal to sign or not. But dead giveaway, not continuous, not differentiable. Next, he wants to graph this. So the graph should be 3 when x is less than 1. So here's 1, 1, 2, 3. So it's just going to be like this. and then -1 when x squared at 1. So -1 is down here, open circle this way. Again, open circle because it's not continuous, not differentiable, not differentiable. Sorry, is it differentiable? No, it's not. So e f of x is not differentiable at x equals 1. If you want to put a reason why, you can set a limit as x approaches 1 from -3. Whoops. Of 3 does not equal the limit as x approaches 1 of -1. So there we go, that's the first one. Oops, sorry. Let's move on to the next one. Same concept. First, it wants to graph this, so cosine of x where x is greater than 0. So remember, cosine, oh, it's a little small. I'm going to say this is, whoops, sorry. Let's go by 2. So this is 1, and then this is 2, and this is 3. -1, -2, -3. Otherwise, it would have been way too small. So cosine looks like this. Not my best graph of cosine, but since that effect. That's what cosine looks like, right? Starts at 1, starts at the amplitude, goes down and up. 1 minus x squared, also known as -x squared plus 1. So that's going to start here also. And then just go up and down. It looks kind of like this. So we're only doing the left side in closed circles, so it looks like this. So it looks continuous, right? They're both going to hit at 1. If you can tell if you plug in 0, cosine 0 is 1. Plug in 0 here, I get 1 minus 0, which is 1. So this does look continuous. So second, we got to go through 3 steps now. We got to find f of 0, which plugs into the bottom one. And that is 1. Check. 2 is the limit as x approaches 0 from the left of f. That equals 1. Limit as x approaches 0 from the right of f. That also equals 1. So the limit as x approaches 0 of f equals 1. Check. So 3, yeah, f of 0 equals the limit as x approaches 0 of f. So it's continuous at x equals 0. So it is continuous at x equals 0. Now we're going to take a derivative. So derivative cosine is negative sine. The derivative of 1 minus x squared will be negative 2x. And again, this is all going to be at x equals 0. We just don't know, I'm not sure about the equal to sign yet. Because it is continuous, so it might be. So it's like a maybe. It may be differentiable. You gotta make sure it's not. You gotta make sure it's not like a pointy line like that. That's why it's, even though it's continuous, it might not be differentiable. You gotta make sure it's not one of these guys. So you can look at it and go, oh, it's not one of those. It should be differentiable. But let's do it mathematically. And the way you do it mathematically is you take the limit at both sides. The limit as x approaches 0 from the left of f of negative sine of x. So I get negative sine of 0. Negative sine of 0 is 0. I need the limit as x approaches 0 from the right, which gets me negative 2 times 0, which is 0 also. So it does check. So it is differentiable everywhere. Remember, most things are differentiable. It's not differentiable at that certain spot. Like this is differentiable here, here, and here. It's just not at this one spot. Actually, let's put the inequalities up there. So it'd be greater than, and then remember it is differential area. So do put the equal to sign because the limit didn't match on these two guys. And then we have to draw it. So negative sine of x. So again, we'll go by 2's. 1, 2, 3, 1, 2, 3. So start at the origin, go down, and then go up. Something like that. And then negative 2x. So search right here. So it'll be negative 2. So down 2 over 1. That's positive, so be negative. So right there. Right there. So it looks like this. So it's kind of like that. So you can see it's nice and differentiable there, and I got this graph. Next one, we're going to do the same thing. So step 1, let's graph it. 3 minus x, so also known as negative x plus 3. So plus 3 down 1 over 1, down 1 over 1. Okay, what do I want? I want greater than x is equal to 2. So here's my x, here's 2, so close circle, and I want the rest of this side. right? So greater than means to the right, so the right side over here, and then I want this the rest of that graph, so I don't need any of this. Less than 2, I want 0.5x, so also known as 1/2 x plus 0. That's what I always do if I don't see a y-intercept at 0. Makes it easier for me. So start right here, and then slope over 2 at 1. Over 2 at 1. In this case, I want the left side of it, so it's going to be like this. So that looks continuous again, but I'm not sure if it's differentiable. It looks kind of like a corner. So it does look continuous, so let's do that part first. So 1, what's f of 2? F of 2 is 3 minus 2, so it's 1. 2, so the limit as x approaches 2 from the right, which we know is 1. The limit as x approaches 2 from the left of 0.5 of x. That equals 0.5 times 2, which equals 1. So the limit as x approaches 2 is 1. And then 3, f of 2 does equal the limit as x approaches 2. So it is continuous at x equals 2. Right, that's all we're proving. We're proving it's continuous at that one spot only. That's all we're doing here. Let's find the derivative. So take the derivative of the top here, I get -1. To the bottom here, I get 0.5. And it's going to be x is greater than 2 and x is less than 2. I should be doing this because we do know that for sure. Like, the only thing we're not sure about, do I include the equal sign or not? That's the only thing, or the equal to sign or not. So how do we do it? We take the limit, right? So it is continuous, so it might. So continuous means it might be differentiable. That's all it means again. It just means it might be. So how do you tell? You do the limit of both sides. Take the limit as x approaches 2 from the left of -1, which is gets me -1, and the limit as x approaches 2 from which is actually from the right. 2 from the left will be this guy, 0.5, which just gets me 0.5. So these do not match. Does not equal the limit as x approaches 2 from the right of f prime. So these actually do not match, so it's not, so not differentiable at x equals 2. So it's not differentiable at x equals 2, so I do not include the equal to sign, but I do still have to graph this. Here's my x, here's 2. Greater than 2 is at -1, so like closed circle, open circle. It's not differentiable. So open circle going that way, and then 0.5 open circle going this way. So there's our graphs. So right, I did the same thing we always do, right? Show it's continuous, done. Then, I graphed it first, and then show it's continuous, done. We took a derivative, so that's just easy to take a derivative of each one of these. Put the same inequalities. You just not sure if you include the equal to sign yet or not. How do you tell if you do the equal to sign yet or not? Take the limit, right? If the limit matches, you put the equal sign. If it doesn't match, you don't put it. If it's discontinuous, you don't put it at all because it can't be differentiable. So that's how it goes. Next one. We're going to graph e to the x when x is greater than 0. So e to the x looks kind of like this. So we want where x is greater than 0. So I want closed circle here, this side. So it's going to that effect. Then we have x plus 1. So x plus 1, start at 1, slope of 1 over 1. Down over, and we want the left side of this one, so it's going this way. So that looks continuous again, but let's go through the steps. F of 0, that is e to 0, so that's 1. Step 1. Step 2, we look at the limit. The limit as x approaches 0 from the right, which we just figured out was 1. Limit as x approaches 0 from the left of f, which would be 0 plus 1, which would be 1. So that they do match. So limit as x approaches 1 of f is 1. And then 3, they do match. So f of 0 does equal the limit as x approaches 1 of f. So it's continuous at x equals 0. Next, we take a derivative. So just try to take a derivative. Derivative ex, it's just ex. Derivative of x plus 1 is 1. Then remember, we copy this, but we don't put the equal to sign yet because we're not sure. Right, how do we tell the equal sign? Well, we gotta take the limit. Because this is continuous, we gotta take the limit. If it was discontinuous, it just wouldn't be. So let's take the limit as x approaches x approaches 1 from, actually 0, what am I doing? We're going to 0 of e to the x. So 0 from the right, which would just be e to 0, which is 1. The limit as x approaches 0 from the left, which is just this equation, which is 1, so that's going to be 1. Hey, they do match. So it is differentiable everywhere. Alright, so it's differentiable everywhere, because it was differentiable before, but it's not that spot. So, I can put the equal to sign on there. That's the big get. Hey, it's differentiable everywhere. I can put the equal to sign. Now we just gotta graph it. ADX we talked about, we don't graph that. It looks like this. That's ugly. Since that effect. And then, well, y equals 1 when x is less than 1. Well, y equals 1 looks like this. So they touch right there. So there we go. Differential everywhere. Next one. Last one of this type. So let's go through real quick. Let's graph negative x squared minus 1. So minus 1, it's a negative x squared, so up and down. Now I'm doing a kind of a sketch, but if I want to do it a little nicer, since this is kind of the way it looks, right? It's going to go both ways. But I want to make sure I know what that point is at 1. So I'm going to do sub 1 into the equation. So negative 1 squared. Well, 1 squared is 1, and then negative, so negative 1. Negative 1 minus 1 is negative 2. So I should be at 1. I should be at negative 2. It's right there. And then it just follows a parabola. So I want the left side, so it's like this. So something like that. Best I can do with my drawing skills. Something to that effect. Next one, negative 2x when x is greater than 1. So I always think about negative 2x plus 0. And then slope of down 2 over 1. It looks like the same spot, down 2 over 1. So, like that. So I'm only connecting it all the way up to 1. Looks something like that. So it looks continuous again, but let's show it. So f of 1, let's plug into this guy. I get negative 2. Then we're going to step 1, step 2, let's look at the limit at both sides. Limit as x approaches 1 from the left, which would be this one. So we know that's negative 2. Limit as x approaches 1 from the right of f, which is this guy. So that'll be negative 2 times 1, which is negative 2. So they do match, so the limit does exist. And they do match. F of 1 does equal the limit as x approaches 1 of f. So it's continuous at x equals 1. Boom. Taking a derivative again, to me that's the easiest part. You just take a derivative. So this would be negative 2x when x is less than 1. Remember, I'm not sure if it's differentiable yet, so you gotta leave it without the equal to sign for now. Derivative that to negative 2. Right, so that was negative 2x, sorry, and this is negative 2. And it does look like differentiable, right? If I plug in 1 there, it's gonna work, so it's gonna be good. Limit as x approaches 1 from the left of f prime is negative 2 times 1, which is negative 2. Limit as x approaches 1 from the right of f prime equals negative 2, so they match. So it's differentiable everywhere. Okay, so on this graph here, let's graph it real quick. Negative 2x plus 0. So 0 minus 2 over 1 minus 2 over 1. Right, but I only want less than 1. So I want to go to the left side. So it's going to be going up actually. Look in the graph. So we're starting at 1. So here, and then we're going to go to the left, which is actually up. And I almost forgot, it's differentiable everywhere, so I got to put the equal to sign. Something like that. Next one's a negative 2. So we know negative 2, it's a straight line across, so like this. So there's our graph for the differentiable everywhere function right here. Okay, let's move on to the next part. If possible, find the missing values needed to make each piecewise function differentiable. Oh, this is one of my favorite questions. I love these guys. The key thing to remember here, if you want to be differentiable means two things. It means continuous plus differentiable, right? So what does continuous mean? Well, that means f of 1 in this case checks, and the limit as x approaches 1 checks. And then differentiable means the limit as x approaches 1 of f prime checks. Right? So we have all that to work with. So a lot of times the first thing I do here is just write the derivative function. So this would be 6x plus 4, where x is, now again I want it to be differentiable, so yeah, that's like 1. And then take the derivative of this guy will be 4x. Remember, plus bx, b is just a variable. Sorry, it's just a constant. We just don't know what the constant is. Different than a variable. Variable could be any number you want it to be, like it could be many numbers. B is a constant, I'm just not sure which constant it is. So the derivative of bx is just b. So the derivative of 3x is just 3. And it's for the same reason, see this a number, goes away. So I have this thing. And now remember, if I want it to be differentiable, it has to be continuous and differentiable, which means that here, these guys should match. If I take the limit of this guy, these should match at 1. So I'm going to say 3x squared plus 4x equals 2x squared plus bx plus c. Right, because this guy. And now I'm plugging 1. So I get 3 plus 4 equals 2 plus b plus c. So 7 equals 2 plus b plus c. Subtract the 2. 5 equals b plus c. So we have this to work with. What about how do I solve that? Well, we'll have another equation here. And it's the same idea, right? If I want it to be differentiable, these two things have to work. So we're going to set those two equal to each other. Right? Because I want this to be true. And then it's true at 1, so you plug in 1. So I get 6 plus 4 equals 4 plus b. I'm going to cancel out the 4s, that's why it works. 6 equals b. So now I have 6 equals b. I could plug this into here. Get 5 equals 6 plus c. So subtract 6. C equals negative 1. So b equals 6. C equals negative 1. Done. Let's do another one of those, because those are fun and I like them. So same idea here. I believe this is the last question on the thing. Right, so they want us to be continuous and differentiable. So first step, take a derivative. So this is going to be, that is the worst. There we go. 2ax, right? The derivative of ax squared is bring the 2 down, subtract 1 off. This is when x is less than 2. And over here, take the derivative, so that'll be negative 2x minus 6 when x is greater than 2, equal to 2. And again, I want this side to be continuous because it has to be differentiable. So all I'm going to do is set them equal to each other. Ax squared plus 10 is equal to negative x squared minus 6x plus b. Right, and I'm going to sub in 2 because that's where I want to be continuous at. I want it to be continuous. Add 2, plug in 2. So I'm going to get 2 squared is 4a plus 10 equals, remember the 2 squared goes first, so 4, negative 4. 2 times 6 is negative 12 plus b. So let's do a little math here. 4a plus 10, negative 16 plus b. How do I want to do this? Let's add the 16 to both sides. So 4a plus 26 equals b. That's a 6. I'll stop there. On this side, right, I want it to be differentiable, so same idea. So they have to equal each other. 2ax equals negative 2x minus 6. And we sub into 2, because that's where we want it to be differentiable at. So I get 4a here, because 2 times 2 times 2, minus 4 minus 6. Right, that's a 6, not a b. I know it's confusing for my writing. So I get 4a equals negative 10. And I get, oh, nothing nice. A equals negative 10 over 4. Also known as negative 5 over 2. I'll tell you right now, that is the right answer. Look at the key. It's the right answer. This sucks. So now plug in for the over here. So 4 times negative 5 over 2 plus 26. Add 26. Almost said 2b. And then this cancels out, and I get negative 20 over 2, so it's a negative 10. There we go. Negative 10 plus 26 equals b. So 16 equals b. So there's my answers. A equals negative 5 halves, and b equals 16. Done.